Here we go, 2215. This is chi-square test. So, goodness of fit. So, chi-square goodness of fit. Okay, now this is where we're always comparing some sort of distribution to a known published distribution or population distribution or something like that. So you have to think that way so that when you're reading the problem, you know where you're going with this. So police use minor violations such as not wearing a seatbelt to stop motorists for other reasons. A large study in Michigan first studied the population of drivers not wearing seatbelts during daylight hours by observations of more than 400 locations around the state. Here's a population distribution of seatbelt violations by age group. So this is my population distribution right here. Okay. The researchers then looked at court records and called a random sample of 803 drivers who had actually been cited by police for not wearing seatbelts. Here are the counts. So here's my sample. Okay. And here's what we got for my sample. And we want to see, does this sample match up with the population? Now what we've done in the past is, or we did yesterday actually in class, is we said, hey, is the distribution of what's published, is it accurate based on my sample? Okay, well, we know this is accurate because it came from data, right? So we can also ask the question, do these two just agree with each other, right? And that's what this question is saying. Does the age distribution of people cited differ from the distribution of all ages up here? Or, in other words, do these distributions differ or are they the same? Okay, so let's go ahead and write this up and put it in words what I just said. So H0 would be the distribution of seatbelt violators is, I'll say, as published or in agreement with the population distribution. Okay, so does it agree with that? And then HA is the distribution of seatbelt violators is different than what is published. Because I can't really say question this right here because that came from 400 locations. This is actual data. I can just question, hey, is my 800, does it agree with it or not? And if it doesn't agree with it, then I can question, okay, where did the data come from? Are the police stopping people in different age groups for different reasons, than what the whole state is? Are they discriminating against a particular age group and so forth? Okay, so the conditions. Is it a random sample? And, yep. Secondly, are the data counts? Yep, data are counts there. And thirdly, are the expected counts greater than 5? Well, we have to verify that once we look at our figure out what those are. So we're going to have to look at chi-square, and chi-square is the sum of the observed minus expected squared over the expected. And I'm going to go ahead and write out what they are. The observed and the expected. Well, I observed 401, 16 to 29, 382, and 20. Okay, that's these guys here. Well, how many would I expect? Well, I had 803 total. Well, how many would I expect 16 to 29 here? Well, I would expect 32.328 times 803. So I'd expect 263.384. I'm not going to round these, so I want this to be exact. I would expect 0.594 times 803. I would expect 476.982 from the middle column, which is 30 to 59. And I would expect 0.078 times 803, 62.634. Okay. So just from looking at this, boy, it sure looks like what I expect and what I got are different. Okay, so now let's put these in here. Let me see if I can. Oh boy, sorry. I'm not trying to get my. There we go. So I'll get up. Get my calculator up and see if we can't do my chi-square test on here. Oh, look at that. Okay. Yes, I'm having some technical difficulties. Okay, so let's do chi-square. Goodness of fit. Just down the road a ways. Oh, goodness of fit starts with L1 and L2, observed and expected. So I've got to put observed. L1, clearing the list. I expected, so observed 401, 382, and 20. And in L2, this way expect 263.384, 476.982, and 62.634. Okay, so now I can do stat test chi-square. Goodness of fit. L1, L2. Degrees of freedom. One less than the number of categories. I have 3 categories, so it's going to be 2 degrees of freedom. Calculate. And I have to report out chi-square is 119.8. And the p-value, that's a big number, is 9 times 10 to the negative 27, so that's essentially 0. That's approximately 0. Okay, so since the p-value is approximately 0 is less than 5%, this is strong evidence that the distribution of seatbelt violators is different. Seatbelt violators. Now, where is this group located? Does it say? would say. Thought maybe this was like in some special town or some specific town or something. Okay, so let's start that the distribution seatbelt violators. Here, we'll go back here. Look right up here. Is different than what is published for the state. So this is what would allow somebody to say, hey, things are a little bit different here wherever we're from, or whatever area or region or something like that. So something's going on with our practices for pulling people over. Okay, and you can tell right here that even in this first one, this contribution here, that 71.9, that's the first entry that over here, if you look over here, that's going to be the first entry for the difference between observed minus expected, squared over expected. That's a big difference that is adding up to contribute to the 119. And so we can't go up to there and look at that and see what that list is. There is a way I think we can do that, and I'll show you this in class. I think, yeah, there it is. It comes up in list, and we can actually look at it, I believe. Yeah, there we go. And I can see the first is 71. I don't know how to, I'm going to have to figure this out and see how to do that. And I'll show you how to look at the rest of it. I'll figure this out and show you in class so we can look at all the different entries and see which component contributes the most to chi-square, and then you can see which age group is the furthest off. Okay, which one's getting pulled over the most. All right, there we go.